All right, we're back. We are Game 2005. That's game physics. And we're in the fall 2017 semester at George Brown. We are week 1, part 2 of our broadcast. Intro, a bit of an intro, who I am. I'm trying to meet as many as I can today of you, as well as we're talking about trigonometry. Again, I know for some of you it's very straightforward. Some of you have even either taken it recently or whatever. But remember, this is a course that's supposed to cover or blanket everyone, so everyone's on the same page. All right, so triangles. Right, we talked about triangles a little bit. Let's keep talking. Again, you missed something in the PowerPoint, you can always go back, right? Okay, let's look at naming as well as the Greek alphabet a little bit. I'm a Greek guy, so, you know, you're going to get Greek anyway, right? And in math, they use Greek symbols all the time. Notice here that we have alpha, and it says beta, but it's actually in Greek we say vita, right? But all the Greek alphabet's used because they don't want to use regular, the regular alphabet, because you might get confused. That's the whole idea, right? So in the book, they have an appendix that goes over the Greek alphabet. You won't need a lot of it. You might need theta for angles most of the time, and you might need phi or phi, right, is what they call it, as well, for alternate angles. I might have 2 angles. I can't use theta for both of them. It might be something else. But for the most part, this is the way we would name our triangles, right? So we have, let's say, vertex ABC. We have an angle ABC, right? If I look at the angle ABC, that means I'm looking at the beta angle in this particular case. Would you agree? Right? If I said ACB, then I would look at the gamma angle, right? And a lot of times I might say, there might be a question, and this is where it becomes tricky. I'll give you a question on an assignment. It'll say, taking a look at triangle ABC, that means the angle is the beta angle that I'm looking for, right? So this is the naming. We use lowercase letters. Sometimes we can also not just use an angle, but you might see an actual triangle in there, triangle ABC. What does that mean? It means that it's just a triangle I'm getting you to look at. There's different kinds of triangles. One of the things to note is the interior of any triangle has to add up to 180 degrees, right? And for the most part, we want to focus on special triangles, right, to help us solve problems. And there's 3 types of triangles. There's the equilateral triangle, which is all sides being equal. If all sides are equal, all angles are equal. And if we have 3 angles and they have to equate to 180 degrees, it means that the angles must be 60 degrees each. Okay? 60, 60, 60. 3 times 6 is 180, right? And this is how we do it, or 18. Multiplied by 10 is 180. There we go. And then we have this isosceles triangle where 2 sides are the same length and 1 side is not, right? Most often the cases, actually all the cases, you notice that this angle is going to be probably an acute angle or a smaller than 90 degree angle. And then a large part of our triangles look like this, where we don't have, actually most of them look just like that, and where we don't have an equal number of sides, or sorry, sides with equal length. And what we can do there is we can split the triangle into 2 other triangles, both with right angles, which we'll talk about this. Special kind of triangle, right angle triangles. We're going to use them a lot, especially when it comes to things like determining the normal of a side, of an edge, or of a particular face when it comes to 3D. So we have a face, the normal points away from the face at right angles, right? That means 90 degrees to the face, or 90 degrees to the edge. That'll be your normal, right? Normal is unit length, length of 1. We're going to be talking about that. 2 things we have to talk about when we talk about triangles is there are legs and the hypotenuse, right? So leg A, alpha, or A and B here in this particular case, and the hypotenuse H, right? All triangles have this. This is a special triangle because it's right angled. And with right angle triangles, we can get to the point where we can use the Pythagorean theorem. And that's why we use right angle triangles for almost everything. If I want to find the distance between 2 points, if I want to find the next position that my ship is going to be in manually in pixels from one position to the other, I can use Pythagorean theorem for this, right? To calculate the next pixel, right? Multiplied by the speed of the ship. So if my ship is traveling, as an example, at a speed of 5 pixels per frame, right? Stop me if you don't understand what I'm talking about. Pixels per frame, right? Because our time sequence, our time sync, when it comes to game making, is every frame. Most frames, we usually run things at, what's the frame rate nowadays? 60, right? Hopefully we try and run a 90 if we can, sometimes, especially when we want to run VR, right? What's the VR rate? Anyone know? Want to try run over 90 frames per second if you want to do VR. Why? Because the flicker rate will be too high. As you come closer, as that thing comes closer to your eyes, right, you can detect the different, the flickering. So most, kind of VR, headgear and all that kind of stuff is already trying to match 90 frames per second. PS4 Pro, they came out with, PSVR, right? And if you run it on your regular PS4, you can see there's a difference. There's a bit of a lag, right? But the Pro, it's not so bad. It's not perfect yet. And in fact, VR, in my opinion, is nowhere near where it should be yet. It's getting there, that's for sure. But when it comes down to price, we'll see more of it. So again, so when I say pixels per frame, that means if I run at 60 frames per second, for this class, let's just assume that it's going to be 60 frames per second when I talk about physics or movement, right? And if that's the case, that means we're going to have a change or a refresh of the screen every 16.666 milliseconds, approximately, right? That's what it's going to be. So every 16 milliseconds in a little bit, you're going to have a refresh. The screen is going to redraw itself over and over again. It's going to render or re-render the objects that are physically inside the camera's view, right? Anything outside the view of the camera is going to be on the screen or in the game world, but not rendered, right? So when I move something, an object, let's say a spaceship or an enemy, and I want to move it from one position to the other, right, in a particular angle of attack, right? I need Pythagorean theorem. I'm going to use Pythagorean theorem to find the next pixel, right? And it's going to be a right angled triangle I'm going to be using every single time, okay? So this is why it's critical to understand this stuff. We're just really talking at a very high level right now, but the devil's in the details, as you will see, right? Because when we want to try and change position, it's really important. All right, again, if we know that all triangles are 180 degrees inside, so all the angles in a triangle must add up to 180 degrees. And if we have a right angle triangle, which means one of the angles is 90, the other two must add up to 90. So alpha and beta, those two angles, must add up to 90 degrees to make up that 180 degrees. Now, this is only for right angle triangles. You're going to get triangles that are not right angled, right? And you're going to try and apply Pythagorean theorem, and it's going to fail, right? Because you can't use Pythagorean theorem for non-right angle triangles, right? So what do? You make it right angled. You split your triangle into pieces until it becomes right angled, and then you can use Pythagorean theorem. That's the way to do it. Or you can use the sine and cosine laws, which we're going to cover at a very high level. All right, so who is Pythagoras? He's a Greek guy, right? Not like me. He's a Greek guy who's like crazy philosopher. He discovered all kinds of things in the age of discovery back in the ancient days before the current era. That says 569 to 494 BCE, before the current era, way back. So we're talking about more than 2,500 years ago, around, or in that range, right? Long time ago. He was a smart guy. And then, of course, René Descartes, he kind of picked this stuff up, and he extended the Pythagorean theorem and mixed it with algebra to kind of create this Cartesian, kind of plane. He used the Cartesian plane to map everything in 2 and 3 dimensions. Okay, so here's the example that I talked about. Why is Pythagorean theorem really good? One, because you see it in nature everywhere, right? We see it at right angles all over the place. If you actually look, whether it's at designs, if you're looking at the golden ratio, all kinds of stuff, it exists everywhere, right? So right angles, the way motion works, and especially because we have gravity, right? We're going to be talking about gravity when it comes to physics. We have gravity dragging us towards the center of the Earth. We have centripetal motion, right? Centripetal force as we move around the Earth, right? And when it comes to angular momentum and angular motion, it's all at right angles. We'll talk about that later on, okay? So another reason is because we have a lot of stuff we can do with it. We're going to talk about what we can do with it later on. And a third reason, of course, which to me is really cool, is you can take a non-right angle triangle, split it in the middle somewhere, and create two right angle triangles that you can use to calculate and to use the Pythagorean theorem. If I have two triangles like this, as an example, right, and if I know the distance between A and, let's say, at the bottom of A, down here, which let's just call this P, right, a point AP, we know the distance. Once we know this side, right, we can almost figure out, if we know the angle, we can figure out the other two sides. And if we know those kinds of things, well, then we can go into, actually, we would know this is 90 degrees, right? So we know 90 degrees. These two must equate to 90 degrees, right? And so, of course, there's something called, these are sister angles, if you will, right? Because whatever is left over in here is going to add up again to make up the 180 degrees for these three angles. And you can use those three things to calculate or figure out, solve, if you will, a triangle, which we'll be talking about. All right. So Pythagorean theorem, one of the basic equations is a squared plus b squared is equal to c squared, right? So when we take that away and we solve for one of the sides, doesn't matter which side, by the way, right? So if I want to solve for the hypotenuse, that's c, as an example, and that's the next pixel, right? If I know a squared plus b squared, right, and if I can take it under the square root like that, I will get c. The problem is we do not want to use square root as much as possible. Now, in this particular case, if I want to find the next position for the pixel, I have no choice, my friends, right? Because a square root is optimized in the machine, right? If I try and make my own square root, I will have a hard time. It'll actually be less efficient than me using the square root function. But if I'm calculating collisions through distance, for example, I want to find the distance between me and you, right? And if I use Pythagorean theorem every frame, 16 frames per second, and I'm using square root every frame, that's crazy. Especially if I have all of you as my enemies and I'm the player, right? There would be a lot of calculations, and it doesn't make any sense. So we would use other forms of collision detection, right? And or I wouldn't have to take a squared plus b squared is equal to c squared and convert it into this form, where c is equal to the square root of a squared plus b squared, but rather keep it in this form here, because it doesn't really matter, does it? If I keep it in this form, if everything is working with this form, and if I just say a squared plus b squared, the sum of the two sides, right? So if I say in a right angle triangle, let's go back to the right angle triangle as an example, right? And if I say, well, look, I want to go this way and this way, right? So here's negative x and or negative x and negative y on a screen. Remember, negative y would be up in a screen. And I'm going from here, from B to A, as an example, right? In this negative direction, right? And if I'm calculating the distance from a collision detection perspective, then I don't care to convert it to a square root. Because at the end of the day, if we leave it in its normal form, right? A squared is equal to b squared plus c squared, or anything else like that, it'll be the same. And we'll see that later on. But however, if I want to find what the next pixel is going to be, then we're going to have to use square root, right? Why is that relevant? And I'll tell you why. Because, and again, unless you use something like gradients as an example, which is another way of doing it. What were you going to say, Hercules?
I was going to say, why don't you just leave things in terms of horizontal and vertical displacement?
Well, it doesn't always work like that, right? For example, if I have unlimited angles, the question is, why don't I leave it in horizontal and vertical displacement? Yes, you can break it. You can break it into components. Absolutely, we want to try and do that as much as possible. However, it's not always possible. If I'm going to go from one position to another in the next frame, right? The easiest way for me to go is to find out the next angle using sine and cosine, right? So I could do it that way. I could use Pythagorean theorem if I want to find the distance. But if I want to find the next position, I'm going to use sine and cosine, and we're going to talk about how to do that. All right, let's continue here. But you're right. It's better to break it down into components. Okay, so triples. This happens in nature. You're going to see 3, 4, 5 triangles, right? If I give you this on an assignment, if you see 3, 4, 3, 4, you know the hypotenuse is going to be 5, right? You should be able to recognize some of this stuff. The two most common ones is this one, and I've given you another one on here. Here's everything, all the triples under 100. Okay, so for example, 3, 4, 5, 5, 12, 13 is very common as well. We see that a lot, right? And there's others here. Also, keep in mind that these could also be ratios. What do I mean by that? I mean, that could be 30, 40, 50, right? As long as the ratios are the same, right? And the angle, the amounts will be the same as well, right? So keep that in mind because, you know, we're going to see this more often. So 90, 400, 410, right? That might be a, you know, a right angle triangle, triple, right? And the way we write it is leg, leg, hypotenuse. That's what we look at it, right? So the hypotenuse, the long part of the triangle, right, is the third digit, okay? Just so you guys know. So if you see this kind of stuff, you might see some of these triples on your assignments and your tests. Don't be surprised if they work out exactly because it's made for that. It's made for you to understand the concepts, not necessarily try and do to figure out the math. What if they come close? Like, for example, you figure out, you know, pi, but, you know, it's going to be approximately what it's supposed to be, and it's some kind of triangle that I'm using, and you're close to the triple, you'll be okay, all right? Remember that I'm going to make you round to probably the nearest 2 decimal places, right? There's going to be a % of error when it comes to what we're doing. But it doesn't matter because from a pixel to a pixel, you either have 1 pixel or 2 pixels. It's a pixel. You can't break a pixel in half, right? If you think about it, when we're moving in 2D. Not really. And I'm going to say not really because it's not wrong to keep track of the extra fraction, right? And the reason for that is because you want to show smooth motion when you do your stuff. But we'll get there. Here's other 2 common right angle triangles you may see in your assignments. I might show these to you as well, right? Where you see this 1, 1 root 2 triangle, right? So 2 sides are 1, the 2 legs, then the hypotenuse must be root 2, okay? That should be something, if you can memorize anything, these kinds of triples, 3, 4, 5, you see a 3, 4, 5 triangle, right? As long as it's got a right angle triangle, you know if I give you 3 and 4, the answer is going to be 5. For solutions, quick solutions, it'll help you cut your time down on an exam or a test, right? Or 1, 2, root 3. That's a very common triangle as well. And it also, you should know, if you think about it, those are the angles. Take a look here. 1, 1, root 2, you know it's 90 degrees, right? And if it's 1 and 1, what kind of triangle is that? The one on the left. We talked about it, right? Isosceles, right? That's the one and only isosceles triangle that is not, right, acute. Because if it's bigger than that, it can't be an isosceles triangle anymore, right? It's going to be weird. It won't work out the same anyway. So take a look at this, right? It's really kind of cool. And the same thing goes here. 1, 2, root 3, 60, 30, and 90, right? And that's a great little triangle as well. So these things occur in nature, but they're some of the most popular triangles. And, you know, you'll see them on assignments. You'll see them on problem questions, practice questions all over the place. So when you look at them, you go, okay, it's 1, 2, root 3 triangle, or it's a 1, 1, root 2 triangle, or it's a 3, 4, 5 triangle, right? We're going to see them all over the place. I'm not talking about now. I'm talking about in physics. An example of that would be if I have a weight that's pulling down on a wire, right? And I have 2 wires, right? I have the tension that I want to figure out the tension between one wire and another one that's holding a weight. There's 2 different types of triangles, both right angle triangles. How do I figure that out? Right? We're going to break down these problems as we go forward in this course to make it easier for you. We're going to use some of these basic triangles to do that, to make it easy. All right. When we talk about gradient, the other word that we use is slope. Those are the 2 words you'll see. Rise over run, the slope of a line. And a lot of times you can find the slope of the hypotenuse, right? We want to find that. One of our students last semester says, hey, I don't even use Pythagorean Theorem. I use, you know, rise over run, like what you're saying, right? I use the components, right? And I can figure out what the vector is going to be, right? And I don't have to use Pythagorean theorem. That's fine too. More complex a little bit in some ways. But what's rise over run, right? Run into, when we think about run, I'm just using, guys and girls, please forgive me. I know some of this is basic, but I got to review it with you. So run, what's run? It doesn't say it here, right? The x, on the x, the horizontal, right? And rise would be the vertical, right? It's very simple. So you take your rise over your run, right? Rise over run is your slope or your gradient, and that's actually equivalent to your tangent. The tangent line is what we're looking at a lot of times when it comes to, especially when we want to get the tangent to a circle and so on, it's rise over run. So here's an example of this figure, right, which is a right angle triangle. We're going to see these graphs all the time. You're going to see, I'm going to draw something out like this. I was talking to one of my professor colleagues, and one of the things he says is that in Asia and different parts of the world, they figure things out differently than we do here in the West. And one thing they do is they draw a lot of diagrams, right? And the idea is if you can draw it, you can figure it out. So Terry, for you to do calculus, if you can draw it out, chances are you can figure it out. And I mean that in a not facetious way. I mean, I really do think that. Doesn't matter if you're doing physics or if you're doing calculus or if you're trying to figure out triangles. If you can draw out the problem, you can figure it out. And that's the first bit of advice I can give you starting off this semester. So think about this graph, what we're seeing here. We're seeing some kind of right angle triangle with a vector xy. That's what the hypotenuse is, right? We don't know what this vector is, what's xy, but we do know, if we know b as an example, that we know that this is the x, because that's x, right? And that's this component, the x component, and this is the y component, right? It's very simple, I know, but people forget these kinds of things. And Pythagorean theorem, we use it everywhere in physics. So please remember to try and draw it out first as much as possible. All right, basic trig functions that we're going to be talking about. I already showed you the basic graphs for sine and cosine and tangent. All right, the idea is that exactly what we just said. Tangent is really rise over run, right? So if I go back to that little triangle, right, it's a over b, right? That's what tangent is. Take a look. A over b, right? And the other ones are a over c, right? That's for cosine. So let's take a look at that triangle. A over c, that's c would be the hypotenuse in this particular case, right? Okay. And then let's go back to the last one, which is b over c. Okay, b over c. So you can figure out, depending on which one you want to find out. If I want to find cosine, right, it's b over c. Well, take a look at that. Cosine is related to the x-axis, right? And sine is related to the y-axis. So if I want to find the distance, the next position of an object in two-dimensional space, right, then I take its velocity, right, which would be the magnitude of this line, right, if we know the magnitude of the line, multiplied by cos theta, right, and we're going to find the next pixel on the x component. So this x component here, right, so v cos theta will give you this magnitude right here, if you know this one already. And you're going to get questions like that. You're going to get questions, well, I have a speed, and this is coming up, by the way, as we talk about particle physics. That's one of the first things we're going to learn in physics, which is, again, I have a cannon, I'm firing a bullet, and it's going across the hypotenuse here. Oops. I'm going across that hypotenuse, and let's say I have a speed of 100 meters per second, right? And I know that the angle down here, if this was I'll ask you guys, a 1/√2 triangle, right? What's the angle down here, right? 45 degrees. If the angle is 45 degrees that I'm shooting my bullet, right? Then what is the x component? It's 100 times cos theta, right? What's cos theta? Which theta am I talking about? Is it this theta that I'm talking about? Hell yeah, it's cos of 45. All right. How do I figure out cos of 45? Well, say that again. √2 over 2, right? So there you go. And there's some stuff we're going to be talking about as we go. And if you think about that, if we get that, whatever that number is, right, that's the x component. And we're going to break it down into x and y, horizontal and vertical a lot of times, right? We're going to use Pythagorean theorem. We're going to use trig to do this. That's why I'm focusing so much on this in this first lesson. By the way, if I've shown you a PowerPoint, I've talked about it, chances are it's going to be on a test, right? Or it's going to be on an assignment. I'm going to get you to do do practice questions. So please, if you just follow the PowerPoints, are you going to pass? No, you need to practice. This is one part of it. Practice, 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 and I'll be giving you some practice questions to do. Okay, so that's the beginning of the trigonometric functions. Let's keep going. It's getting pretty loud out there, which means we're coming to the end of end of class right now. So again, tangent, of course, if you think about this as sine over cosine, which we talked about. And I want you to assume, like we said, that from a computer perspective, it's radians. You need to convert. Here are some trigonometric identities. Do you need to know these? No, but you need to know when to apply them. I will give these to you on a test or an assignment. On assignment, you'll have them. There are some great sites out there that can check your work. That's good, right? That's why assignments, I'm going to give you the assignment. I'm going to give you kind of a question. I expect you to go and get perfect on your assignments. That's what I expect you to do. Go explore and get perfect. If you do it, and if only your partner does the work and you don't do anything on a test, you'll suck. Just letting you know, right? That's why it's really good for you to do it on your own. So let's say, for example, I'm working with Emma. So Emma's my partner, right? I am way out there, right? There we go. So Emma and I are partners. And if I get an assignment, and if I just do it on my own, and Emma, she's not so good at math, or she doesn't like math, whatever, she's busy, she doesn't feel like doing it, I just do it for her. That's really bad, right? Because remember I told you, the assignments are training you for the tests. So if she doesn't know how to do that, and if she doesn't recognize that question on an assignment, on the test, Emma might be in trouble, right? So what do I expect you guys to do when I give you guys partner assignments? Both of you do it. Compare the questions, together. So let's say Emma and I both do it, and then we find out the right answer, right? But we understand how it's being done, so I can apply it on a test. Okay, so these trig identities, what do they mean? One of the most common ones is sine squared x plus cos squared x is equal to 1. You can use some of these trig identities to do things like solve an equation, solve a problem that we have, solve a triangle, all kinds of stuff. Maybe there's more than one triangle that you have to solve. We're going to use these trig identities all the time, right? Especially when it comes to some of the problems I'm going to be giving you. And there's others. This is not a complete list, right? So if you actually look online, there's a bigger list that I'm going to get you to look at. Okay. And I'm timing out, so I'm going to go a little faster. I apologize. One thing to know is that what this does is this gives us, it doesn't give us the angle, it gives us the length a lot of times, right? And sometimes we want to know the angle, and we use the inverse trigonometric functions to find the angle. So we use, for example, arcsine and arccos, or arctangent to find the angle, given what you know, right? So for example, I might have, the information that I might have is, I might be using the sine or cosine law, and moving around the equation, I can find out what the angle is, but I need to use arctan or arccos. By the way, guys and girls, a lot of times it's with radians that we have to figure this out. So here's an example of the sine and cosine rules that you'll see, right? Sine rules, they work great with right angles, right? Cosine law and sine law, right? If you don't have a right angle triangle, if you don't have a 3, 4, 5 triangle, if you don't have a Pythagorean, if you can't use Pythagorean theorem, you have to use sine law or cosine law to figure things out, okay? So an example would be, what the sine law basically says is that there's a proportion between the angle of one part of the triangle with the angle and the length of another part of the triangle, right? So if I have 3 out of the 4 parts that I'm looking for example, let's say I have the angle B and the angle A and one side, right? Angle alpha, sorry, and angle beta, that's right. And let's say, for example, I have one side A, then I can find B. Because it's all in proportion. It's the ratio of the different sides, right? So that's what the sine law tells us. Don't worry if it seems like it's Greek to you. And I don't mean it in a facetious way. If you don't understand what I'm talking about, don't worry. We're going to practice some of this stuff. Okay. All right. And this is the cosine law, which reads a little bit more complex, but at the end of the day, it looks like an extension of Pythagorean theorem. So a squared plus is equal to b squared plus c squared minus 2bc cos alpha, right? Well, why can this work? Well, if alpha is 90 degrees, right? Again, what's cos of 90? And if it's 0, what are we subtracting? 0. So then we're back to Pythagoras, right? Alpha, a squared plus is equal to b squared plus c squared, right? So that's why we add this cosine law when we don't have a right angle triangle, or we're not sure it's right angle triangle, right? We can use the cosine law to do that. So again, why am I saying this? Because there's going to be a time where I want to find the tension between two cables holding a weight that's being pulled down by the gravity, right? By the force of gravity, and they're not equilateral. They're not right angle triangles somehow. It's something odd. It's something off, and you need to use the cosine law to figure that out. For the most part, again, as long as you split a triangle in half like this, so again from point B to P, right? You can make two right angle triangles, and then from there, this would be the height of the triangle, and from there you can find the area of the triangle, which is half base times height, right? If you had all the numbers you needed. In this particular case, you do. So with a length of L, if I knew this length, B to P, and I knew the length L, then I could find the area. Okay, 2 more slides, guys, then we're done for today. I swear, right? And did I just copy this? I did. I love duplicate slides. 1 more slide, we're done. This is serious, guys. If you guys don't know this, if you can't remember anything, if you're going to remember anything to speed up your calculations on a test, it's this, SOHCAHTOA, right? And if you don't remember this from high school, this helps us with all kinds of stuff. So I want to find the angle X as an example, and depending on what I have, if I have the adjacent, so let's say I want to find this angle. If I have the adjacent and the opposite, what do I use to find that angle? So but that's arctan, right? Think about it. Tan theta is equal to, if I look at this TOA, which is opposite over adjacent, right? Tan theta is a number, whatever the number is going to be, right? Yeah, I got to take that number and plug it into the arctan to find the angle, right? So please keep in mind, this is one part of the answer when it comes to finding the angles when you have the lengths of the sides, but it's not the complete answer. You need to do the inverse of the trigonometric functions in order for you to get that. And that's it for me. That's what I have for you today. I only wanted to limit it to 40 slides. I want to keep doing that every time we're together, right? Because at the end of the day, I think it's a lot of material we want to cover. And if I cover it slowly like this, you can eat the elephant in chunks, right? So next day we're going to get together. We're going to start covering things like limits and derivatives, right? That's the next section. And I'm going to try and kind of split up calculus at least into 2 days, okay? It can't just be 1 2-hour session and that's it. Yeah.
Are we going to be able to, like, everything we learned today, are we going to be able to apply practically in the next lab?
In the next lab, which is now, for some of you, I'm going to be doing some setup, and I'm going to be talking about some practice problems we're going to be doing in the lab. Yeah.
So will the lab and lecture go together?
Yes. Yes. I'm going to try my best to do that. In this lab, we're going to have a very short lab because it's an intro. It's the first day. I don't want to kill you guys, right? And some of you, by the way, aren't even here, right? So that's a problem. And to be fair, I can't give you everything to this week, but starting next week, we're going to have labs every session. That's something that you're going to hand in, all right? So not this week, but next week, we're going to hand stuff in. Any other questions? I'll stop recording. For anyone who has anything to ask me, come straight up.